Okay, ready? Okay, welcome back. This is Apology of Chemistry, Module 11. We're actually on page 364 if you want to follow along in the book. We've been talking about the chemistry of solutions. So we're going to take a minute and talk about a couple of terms that you need to know. The first one is exothermic. When you have a solution that gives out heat, exo, like exoskeleton, thermic, heat, it's going to give off heat. The other term is endothermic, and that means it's going to take in heat. It's going to absorb heat. And an example of this, especially this time of year, might be the hot hands that you get when you go skiing. What happens when you do that is you break apart the package and it allows the two chemicals to mix together. And when those chemicals mix, they actually give off heat. Heat is produced in that reaction, so that's an exothermic reaction. And endothermic would be one where when you touched it, after the reaction it felt cold. An exothermic reaction is going to be one where when you touch it, it feels warm. So we'll talk more about that as we go, but we're going to take a minute here and kind of go backwards. We're going to be talking about something that we talked about in the last chapter. We spoke about how stoichiometry affects solutions and how you're going to be using the definition of molarity. Do you remember what that is? Molarity is the number of moles per liter. The number of moles per liter. We're going to be talking about how molarity combines with stoichiometry to help you solve some problems. So there's some examples in your book. Example 11.1 and example has two parts that you can look at. And I'm going to be talking specifically about one of the on your own. So I'm going to be talking about the on your own 11.4. And that's on page 367. Now in the on your own 11.4, notice that we're going to combine that definition of molarity, the number of moles per liter, designated by a capital M, okay, with what we know about stoichiometry. Remember we said stoichiometry is just a fancy name for the recipe of a chemical reaction. It's how things combine. And just like when you're making cookies, if you know that it takes 2 cups of flour and 1 cup of sugar, that's the relationship in that recipe. And it's the same thing with chemical reactions. In this case, we know you have 5 H2O2 plus 2 KMNO4 plus 3 H2SO4, and that's going to form 5O2 plus 2 MnSO4 plus K2SO4 plus 8 H2O, where this number in the front is the stoichiometric coefficient that tells you how much of that is used, how much of that stoichiometric relationship is used. So just like if it was a recipe for cookies, oatmeal cookies, it would be like a 5-to-3 ratio here, or a 5-to-5 ratio here, or 5-to-2, 5-to-1, 5-to-8. For every 5 of these, you would produce 8 of those, just like the same as you would have with a regular recipe. So in this situation, you're given, the question says, you're given 125 milliliters of 0.5 molar H2O2 and everything else you have in excess. And it wants to know how many grams of oxygen are produced. How much oxygen is produced in that reaction. So the first step, what do we always do? You always write your balanced equation. But guess what? You're in luck. They've already done that for you. They've already written your balanced equation for you, so you don't have to worry about that. The second step, you're going to ask yourself, what do you know? Where do you want to go, right? What do you know? Where do you want to go? Well, we've already written this out for you. So we know that we have 125 milliliters of 0.5 molar H2O2. That's the what we know. Excess everything else. And where we want to go is how many grams of oxygen are we going to need? How many grams of oxygen? So we're relating the H2O2 to the oxygen, okay? So the third step is you're going to look at your definition of molarity. Remember we said molarity is the number of moles per liter. And in this situation, you're given a volume and you're given a molarity. So can we find the moles? Yes. We're just going to set it up. We're going to say we have a molarity of 0.5 molar H2O2, a volume of 0.125 milliliters, but we had to convert that to liters. So it's 0.125 liters. It was 125 milliliters, but we had to convert to liters. So it's 0.125 liters. Now, if we know the molarity and we know the volume, we can multiply those two together, and then we can find the number of moles. And then once we have the moles, we can use the recipe to find out the moles of this. So we're almost there. So we multiply those together, and we find that we get 0.06 moles of H2O2 when we multiply 0.5 times 0.125. Okay, that's the molarity times the volume, and that's going to give us the number of moles by the definition of molarity. That's the third step. The step 4, we're going to use stoichiometry. We're going to use that recipe, the relationship between the recipe. And if we look at what we're looking at the relationship between H2O2 and O2. And we find that it's a 5 to 5 relationship. Okay? So we said we had 0.06 moles of H2O2. And we're going to use the stoichiometry, 5 to 5, the moles of O2 to the moles of H2O2. That's going to cancel out, and we're going to end up with the moles of O2, the moles of O2. And we found that we have 0.06 moles of O2. The fifth step, we're going to convert the moles of oxygen to grams. And again, this is just simple stoichiometry, remember from back in Module 5. So we're going to take that 0.06 moles of O2. Now we need to know the gram formula weight, and there's 2 of them. The gram formula weight for oxygen in the front of your periodic table is 16. You have 2 of them, so that's 32. 32 grams of oxygen for every 1 mole of oxygen. And your moles are going to cancel out again. And you're going to find that when you multiply 0.06 times 32, you get 2 grams of oxygen, which answers our question. How many grams of oxygen are produced in this reaction given that amount? Okay, so that's stoichiometry and solutions. Thank you. We'll be back in a minute with more information.